Dr. DN Gokhale is coming. Just 1 minute. DN Gokhale.
Start.
Honorable Visitor, just Dr. DN Gokhale sir is coming. Please 1 minute.
As we are waiting for our guest speakers to join, we start in 5 minutes. Yes, sir, join. Yeah. Shinde sir, is all the speakers joined?
Just wait 1 minute another. Otherwise, we will start. है ना?
Oh,
Yeah.
fine.
Just called. He is facing some issues for joining.
Okay, maybe some
Yeah,
network.
no, yeah.
No problem.
Dr. Shinde. I think we should start now.
Let us start. उसके बाद in the meantime के साथ coordinate करें तो he can join in the meantime.
Right, sir. Right, sir.
Let us commence.
Dr. Dipali, please start.
Okay, sir.
Please go ahead.
Okay, sir. A very good morning to all. Agriculture is the backbone of the livelihood security system of nearly 700 million people in the world. We need to build our food security in the foundation of homegrown food. With these words of M.S. Swaminathan, I, Dr. Dipali Saxena, Assistant Professor of Sri Vaishnav Institute of Home Science, Department of Food and Nutrition, Sri Vaishnav Vidyapeeth Vishwavidyalaya, Indore, welcome you all in Second International Web Conference on the Future of Food and Agriculture, Trends and Challenges, VAKSANA 2021 on 20 to 21 September 2021. Every work remains unconvinced, unmoved, without the blessings of the Almighty. To make this morning a blessed one, may I now request to technical team to invoke the goddess Saraswati by virtually kindling the lamp of knowledge and wisdom and play Saraswati Vanna. Yes, please, technical team.
तमसो मा ज्योतिर्गमय मृत्युर्मामृत्युञ्जय ॐ शान्ति शान्ति शान्तिः या कुन्देन्दुतुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा।
Thank you. Now I request to Honorable VC Sir Professor Upinder Ghar, Vice Chancellor of Sri Vaishnav Vidyapeeth Vishwavidyalaya, Indore, for floral welcome of Dr. T.N. Kokle, Director of Instruction and Dean, Vasant Rao Naik, Marathwada Krishi Vidyapeeth, Parbhani, Maharashtra. Yes, technical team. Same for Dr. D.B. Dio Sarkar, Director of Extension Education, Vasant-Rao Naik, Marathwada Krishi Vidyapit, Parbhani, Maharashtra. Yes, please, technical team. Thank you. Same for Dr. Naresh Silokar, sir, scientist, Indian Council of Agriculture Research, National Dairy Research Institute, Karnal, Haryana, India. Yes, please, technical team. Thank you. Agriculture has been associated with the production of essential food crops. At present, agriculture above and beyond farming includes forestry, dairy, fruit cultivation, poultry, beekeeping, mushroom, etc. But today, processing, marketing, and distribution of crops and livestock products are also acknowledged as a part of current agriculture. Thus, agriculture could be referred to as the production, processing, promotion, and distribution of agricultural produce. Now, without any taking pause, I would like to request Professor Upinder Dhar, Honorable Vice Chancellor and Conference Patron for the inaugural address. Sir, Honorable Vice Chancellor, sir.
Good morning to all of you. At the outset, I would like to welcome our eminent guest speakers, Dr. D.N. Gokhale, Dr. D.B. Jayasarkar, and Dr. Naresh Silokar. I would also like to welcome my colleagues, Dr. K.N. Guruprasad, and all other directors of the university, dean and convener of this program, Professor Vinod Dhar, and my dear young friends, all the students of agriculture and other institutes of the university. I would like to compliment the team at our Institute of Agriculture for having chosen the appropriate theme for VAKSANA 2021, Future of Food and Agriculture, Challenges and Opportunities. I looked into literature that how different authors, different researchers have looked at it. And I could see one report of Food and Agriculture Organization that has dealt with this subject in detail and has also identified various challenges. As we know, the demand for food will continue to increase and will do so in the context of increasing scarcity of natural resources and important changes in the structural composition of the demand for food and agricultural products. Climate change and increased competition for natural resources will continue to contribute to natural resource degradation and scarcity, with negative impacts on people's livelihoods and food security. Problems of extreme poverty, hunger, food insecurity, and undernourishment will persist, along with increases in overweight, obesity, and diet-related chronic diseases. Natural disasters are increasing in number and intensity, and along with climate change related extreme weather events are expected to deepen the global need for humanitarian assistance and resilience building for farmers and rural households. At the same time, transboundary plant pests and diseases and other emerging threats continue to provoke crisis in agricultural and food systems and impact productivity and human health. Conflicts are continuing and could intensify in many parts of the world, with widespread economic and social consequences beyond the afflicted countries. Dynamic rural transformation is happening in most of the low-income countries and is expected to continue. This will have impacts on agricultural production systems, employment, nutrition, and migration, and will present society with the challenge of finding ways to include everyone in the development process. Rapid changes and transitions in food systems increasingly call for effective national and international governance systems and evidence-based and well-targeted policy responses. More investment in agriculture and agri-food systems, including increased spending on research and development, is needed to enhance agricultural productivity and promote innovation for sustainable agriculture, rural prosperity, and food security. Based on the conclusions of the analysis of global and regional trends, a set of 10 challenges are outlined, which are the most pertinent to food and agriculture organizations' mission to eradicate hunger and malnutrition, achieve food security for all, improve rural livelihoods, and make agriculture, fisheries, and forestry and their natural resource base more resilient, productive, and sustainable. The overarching challenge facing food and agriculture will be how to address them as a whole. You see, if we briefly touch upon these challenges, the very first and foremost challenge is sustainably improving agricultural productivity to meet increasing demand. See, as we know, demand is continuously increasing. It is not going to reduce. Demand for food and other agricultural products is projected to increase by 50% between what it used to be, what it was in 2012 and 2050. Demand will undergo structural changes owing to factors such as population growth, urbanization, and per capita increases in income, while the natural resource base upon which agriculture depends will become increasingly stressed. Producing more with less while preserving and enhancing the livelihoods of small scale and family farmers is a key challenge for the future. If we look at the second challenge, say ensuring a sustainable natural resource base, projections for 2050 suggest growing pressures on agricultural land, water, forests, capture fisheries, and biodiversity. Between now and 2050, the additional land needed for agricultural production is estimated at just under 100 million hectares. It is expected that demand for agricultural land will decrease in high-income countries, but increase in low-income countries. This is very interesting observation. The resulting modest increase might suggest that land availability is not a constraint. In fact, increases in the agricultural area is constrained by the fact that available land is not readily accessible due to the lack of infrastructure, physical remoteness, and disconnection from markets, or is vulnerable to disease outbreaks. Furthermore, available land is concentrated in only a few countries. That is why increases in agricultural production to meet rising food demand will have to come mainly from improvements in productivity and resource use efficiency. Third challenge is addressing climate change and intensification of natural hazards. Similarly, fourth challenge is eradicating extreme poverty and reducing inequality. I'm not explaining each one of them because I'm sure that during VAKSANA 2020, that is 2021, today, these challenges will be touched upon by various eminent speakers. Challenge 5 is ending hunger and all forms of malnutrition. In fact, I missed fourth one. Fourth is eradicating extreme poverty and reducing inequality. Now coming to challenge 6, making food systems more efficient, inclusive, and resilient. Seventh challenge, which has been identified by the researchers who have prepared this report of the Food and Agriculture Organization. The seventh challenge identified is improving income earning opportunities in rural areas and addressing the root causes of migration. Eighth challenge is building resilience to protracted crises, disasters, and conflicts. Ninth challenge is preventing transboundary and emerging agriculture and food system threats. And the last challenge identified by the researchers is that addressing the need for coherent and effective national and international governance. Growing competition over natural resources can cause the rural poor to be dispossessed of the very foundation of their livelihoods, especially in protracted crisis situations and conflict and disaster affected areas. A key governance challenge is ensuring the recognition of the poor's formal and informal rights of access to and use of natural resources through implementation of voluntary guidelines on the responsible governance of tenure of land, fisheries, and forests, and through support to the realization of the right to adequate food, especially in the areas that are vulnerable to the impacts of climate change and conflict, and where institutions are fragile. Improved natural resource governance based on the concepts of governance of tenure will be needed to establish a flexible framework for mitigating and resolving conflicts over land, water, fisheries, and forests, protecting biodiversity and ensuring ecosystem services. Other areas requiring improved governance include financing for inclusive food and agriculture development, meeting employment and migration challenges, addressing shortfalls in the multilateral trading regime in relation to food and agricultural systems, and providing open access to data and statistics to enhance the role of all stakeholders in governance. So this area of interest is of great concern. So future of food and agriculture, we need to ponder upon. We need to think about what can be done. We need to prepare ourselves and realize, understand the intensity of these 10 challenges identified by the researchers at FAO. So I'm sure that during VAKSANA 2021, that is today, our eminent speakers will touch upon these aspects and educate all the faculty and students about how to prepare ourselves to face such challenges. With these words, I once again welcome all the speakers and participants to VAKSANA 2021. Thank you very much.
Thank you, sir, for such an informative. Thank you, sir, for such an informative words regarding challenges of agriculture. Now, I would like to request Dr. K.N. Guruprasad, sir, organizing chairperson and coordinator of Sri West Institute of Agriculture, for the welcome address. Guruprasad, sir.
Thank you, Ma'am Dipali. Vice Chancellor, Professor Rupendra Dhar, guest speakers, Dr. D.N. Gokhale, Dr. D.P. Dev Sarkar, and Dr. Naresh Selokar, Professor Vinod Dhar, Dean Madam Dr. Dhar, colleagues and students. At the outset, I welcome all the guest speakers of this conference. I have seen the subjects which they have chosen for their presentations, and a couple of them are speaking on BT cotton, and a person on the cloning of buffaloes from, I guess, the scientist from Karnal will be speaking on that. As the Vice Chancellor has pointed out, where do we stand today in terms of agriculture, and how do we look forward for meeting the needs of food and agriculture in the future. As a scientist, we can see that we are at crossroads right now. For example, BT cotton is a molecular biology intervention in the natural production of cotton. Now, such interventions have been happening even in the food crops in other countries, whereas in our country, we have limited this interference only to cotton, since it's not edible. So we are using this technology, and we are still apprehensive about using this technology in other areas, particularly in increasing the production of food crops. Now, similarly, the use of chemical fertilizers, use of pesticides and others. Now, the adverse effects of overuse of these chemicals are coming into focus now, because of which now there is a promotion of organic food products without using artificial chemicals. But recently I was reading an article on Sri Lanka, where they decided to go completely organic, and because of which their main agricultural products which are exported, particularly tea and rubber, were greatly affected. Now they are rethinking about it because it has affected their economy, since organic farming reduces the production. We have not achieved a technique in organic farming that can match the production that can be achieved with chemical fertilizers or by molecular interventions. So we are at crossroads right now. On one hand, we need to meet the demand of the overproduction, which is there for the next few decades. And at the same time, we also need to balance the adverse effects of overuse of chemicals and the dangers of genetic intervention. So this remains as a challenge for the scientists. And as a plant scientist, I know many of my colleagues are working on this, and they are trying to make the scientific intervention as safe as possible. So there is a need now to have the trust on the safety measures of the scientific methods, and the scientists are working on it, keeping that in focus, but at the same time trying to meet the demand of the food. With this introduction, I look forward for the interesting talks by our guest speakers. Thank you.
Thank you, sir. Now I request the technical team to please release the souvenir of VAKSANA 2021.
Deepali,
Yes.
you need to be louder.
Thank you, sir. Now I request the technical team to please release the souvenir of 2021. Yes, technical team. Thank you. Now we started the lectures of our lead speakers. The first lecture is of the Dr. D.N. Kokle, sir, on the topic socio-economic impact and impact on dynamics of BT cotton in India. Dr. D.N. Kokle is the director of the Instruction and Dean Vasantrao Naik Marathwada Krishi Vidyapith, Parbhani, Maharashtra. Sir, having 30 years of work experience in the area of teaching, research, and extension. Dr. Kokle guided about 35 MSc and 5 PhD agriculture students. Sir is also contributed in research and has given several recommendations in Joint Agriso Release Committee of different agronomical crops such as BT cotton, pigeon pea, maize, kharif crops, sorghum, sunflower, okra, and cropping systems for the benefit of the farmers. Dr. Kokle published a number of research papers in reputed journals. He has been honored with several awards and medals by different recognized NGO and societies, such as Shiksha Ratna Puraskar and Certificate of Excellence, Glory of India, Gold Medal, and Dr. Radha Krishnan Gold Medal Award. Yes, over to you, sir. Dr. Kokle, sir.
Thank you, Deepali madam. Good morning to one and all. Chairman of the today's function, Dr. Upenderji Dhar sir, Honorable Vice Chancellor, Shri Vaishnav Vidyapith Vishwavidyalaya, Indore. Organizing Chairman, Dr. K.N. Guru Prasad ji. Guest speaker, Dr. D.B. Devsarkar, Director of Extension, Vasantrao Naik Marathwada Krishi Vidyapith, Parbhani. Dr. Naresh ji Shelokar, Scientist, ICARI, NDRI Colonel, Haryana. Convener, Professor Vinod ji Dhar sir, Coordinator, Dr. Yuvraj ji Shinde and Dr. Narendra Chauhan, distinguished guests and student friends and my colleagues. I heartily welcome you all for eager participants and eminent scientists who witnessed our second international web conference on the future of food and agriculture trends and challenges. Today, I am here to share my views on socio-economic impact and impact dynamics of BT cotton in India. International scientist from Washington State University, Glenn Stone, said that the first long-term study of BT adoption and production trends at both national and state level shows that BT seeds were not the cause of rising the yields, and that the insecticide reductions were fleeting. The king of fiber, what we call the white gold, that is cotton, which is cultivated in tropical and subtropical region of the more than 70 countries across the world, and enjoys a predominant position amongst all the cash crops in India. The major producers of cotton are USA, China, India, Pakistan, Uzbekistan, Australia, Greece, Brazil, Egypt, and Turkey, contributing around 85% of the global cotton production. Cotton is the major cash crop of India and is the largest cotton cultivating country in terms of acreage and second largest in terms of production. India accounts for 34% of the cotton area in the world, accounting for about 26% of the world cotton production. India has the distinction of having the largest area under cotton cultivation in the world, constituting about 38% to 41% of the world area under cotton cultivation. It is grown under rain-fed as well as irrigated condition, and the major cotton producing states include Punjab, Haryana, Rajasthan, Madhya Pradesh, Gujarat, Maharashtra, Andhra Pradesh, Karnataka, Telangana, and Tamil Nadu. Actually, in India, cotton is primarily used to grow by smallholder farmers with farm sizes of less than 15 acres and cotton holdings of 3 to 4 acres on an average. The first BT cotton hybrids were commercially released in India in the year 2002, and the scenario of BT cotton farmers by 2011 was that 7 million farmers had adopted BT on 26 million acres, around 90% of the total Indian cotton area. Besides, development of hybrid cotton varieties in the year 1970s, which occupy 45 to 50% of the area under the crop, gave boost to its productivity in the past. As a result, the cotton productivity in India increased from 1.06 quintal per hectare during 1970-71 to 2.65 quintal per hectare during 1996 to 97. In Punjab, it jumps from 4.63 quintal per hectare during 1991 to 5.02 quintal per hectare during 1994 to 95, and then followed a downward slide and reached an all-time low of 1.79 quintal per hectare in the year 1998-99, when farmers were not able to recover even the cost of cultivation required for the BT cotton. This was due to the outbreak of American bollworm, Helicoverpa armigera, which is one of the major insect pests of cotton and has developed resistance to pesticide due to selection pressure. To overcome this downward slide in the productivity of cotton crop, many integrated pest management programs were initiated. The regional program on cotton IPM by Commonwealth Agricultural Bureau International CABI in 1993. FAO European Union IPM program for cotton in 2000. National Agriculture Technology Project in 2000 and Insecticide Resistance Management Program in 2002. The focus of this IPM program was to reduce and rationalize pesticide use by encouraging farmers to adopt other pest management practices like cultural and manual mechanical practices in the absence of any effective bioagent. As far as the impact dynamics in modern agriculture biotechnology is concerned, over the last 19 years, modern agriculture biotechnology has been adopted rapidly at the global level, including several developing countries. This trend has been most seemingly for genetically modified crops. This is the fastest dissemination of any new crop technology in the history of humankind. The number of countries growing genetically modified crops has increased from 6 in the year 1996, the first year of commercialization, to 18 in the year 2003 and 29 in the year 2010. The growth rate between 1996 to 2010 was an unprecedented 87 times fold increased by making it the fastest adopted crop technology in recent history. Technological development and dissemination is not an isolated scientific activity. It is influenced by the social, economic, cultural, and political conditions. This holds true for modern biotechnology. As the wider farmer community at global level struggles to come to terms with the benefits and unpredictable risks of the biotechnology. Better understanding of consumer interests and concerns is needed to formulate and implement effective private and public policies. Hence, a successful biotechnological program needs to address the socio-economic issues to ensure that public and policymakers are fortified to make informed choices. BT cotton is genetically engineered with BT, Bacillus thuringiensis, a biotoxin which comes from soil bacterium. BT, which was isolated from soil in the year 1911, has been available to farmers as an organic pesticide since 1930. The engineered BT gene produces a protein that cuts into the guts of specific insects, rendering the cotton resistance to these insects. Biotechnology for control of bollworms is made available in the seed itself. Farmers have to just sow the BT cotton seeds as they do with conventional seeds. The resulting plants have the inbuilt ability to produce BT protein within their body and defend themselves from bollworms. No extra efforts or equipments are needed to utilize this technology. But after the introduction of BT cotton, it is brought into focus a variety of issues like economics, environmental, and health, and it has a controversy against to adapt it. Hence, we are here to focus socio-economic impact and impact dynamics of BT cotton in India. Hence, here with BT cotton adoption, has raised consumption expenditures, a common measure of household living standards, by approximately 18%. It added that BT cotton had created large and sustainable benefits which have contributed to positive economic and social development in India. As far as the impact dynamics of yield advantage technology for enhancing the productivity of BT cotton is concerned, the yield advantages in BT may be due to the BT technology or due to additional inputs used for BT cultivation. Sources of the yield difference between BT and non-BT cotton was estimated by decomposing the productivity chain into technology effect and input effect. The production technology of conventional hybrids and BT hybrids. The existing inputs are used. The yield from conventional hybrid will be as existed, while yield of cotton will be the yield gain due to technology. If the inputs used are increased, then the yield increases for BT hybrids. Hence, cotton yield will be the yield gain due to additional inputs. As far as the economic impact dynamics surplus is concerned, economic surplus approach is widely used for estimating total benefit of a new technology and to evaluate its distributional impact. An economic approach to evaluating research begins with the basic commodity market model of research benefits. So it represents the supply function before the technical change and demand function. Suppose research generates yield increasing or input saving technologies. These effects can be expressed as per the unit reduction in production cost. This research induced supply shift leads to an increase in production, consumption, and the market price fall. Consumers are better off because the new technology enables them to consume more of the commodity at lower price. Impact dynamics of agronomy and environment is concerned. As review about the economic and economic impact of BT cotton cultivation demonstrated that adopting farmers benefits from income increase through reduced pest control cost and higher effective yields. The benefits will vary according to varying pest infestation levels in different years and locations. In the Maharashtra state of India, Narayan Murthy and Kalamkar in 2006 found that the farmers cultivating BT cotton had marginally higher expenditure of pesticides. They argued that the farmers spray the same quantity of pesticides as before because of the fear of bollworm attack. One of the most important characteristics of BT technology is that it reduces pesticide use in cotton. There are different approaches to quantify the environmental impact of pesticide use. The marginal productivity estimate provides an indirect measure of the cost in terms of foregone agriculture output of reducing pesticide use to protect human health and environment. Social impact of BT cotton is one of the most important aspects. Cotton is often the major crop for cotton producing households in India, so that profit gain through BT technology are also likely to increase household living standard. A common way of measuring living standard in the development literature is to look at household consumption expenditures, because expenditure is usually a more reliable indicator than income. Although BT adopting household also increased cotton profit. They did not immediately change their consumption behavior, but waited until they realized that the profit gains are sustainable. Over the last 20 years, the partnership between farmers, seed and biotechnology companies, agriculture universities and scientists, rural trade, central and state governments, and the user industry have enabled India's cotton revolution by doubling production to claim the world's second highest producer and exporter spot. The benefits of BT cotton technology in high yielding hybrid cotton, along with improving farming inputs and favorable market conditions, has helped to create additional value for cotton farmers by significantly reducing insecticide uses and increasing the yield. As far as the economic impact of BT cotton is concerned, the benefit of BT cotton has spread beyond just the farming community. Since 2002, BT cotton technology has boosted the fortune of the Indian cotton seed industry by giving technology access to small and medium-sized seed companies. This has enabled companies to invest in innovation, improve their cotton seed germplasm, and adopt various mechanization options in the fields. Numerous stakeholders across the cotton value chain, that is seed industry, ginners, textile industry, have benefited from the technology. Not surprisingly, over the last decade, while the cotton seed industry, consisting of more than 90% share for Indian seed companies, has grown 8 times from rupees 0.45 billion in 2002 to rupees 40 billion in 2018. The Indian textile industry, which today employs over 0.04 billion workers, continue with large-scale investments. Besides India, farmers in many other nations have benefited due to BT cotton cultivation. Example in USA, China, and Australia. As far as the socio-economic impacts of BT cotton is concerned, several studies by third-party economists, sociologists, and others have established 85% of the hybrid BT cotton seed farmers and farm workers invested in better education for their childs. Near about 77% reported better intake of nutritious food, 75% better health of their family members, and 64% invested on health of livestock. Whereas female workers on BT cotton fields earn average 55% higher income. 42.4 crore additional days of rural employment have been generated in recent years by farmers. The cotton production using hybrid BT cotton seeds on over 90% of us. In a study conducted by IIMA, the performance of BT cotton relating to other factors and input like BT gene, hybrid, pesticides, fertilizers, irrigation, and agroclimatic zone was affected by multicollinearity, but indicated a significant impact of BT cotton as yield determinant. This estimated impact of economics on yield and profitability of farmers was found to be 22 to 35%. As far as the impacts of BT cotton on entomology is concerned, besides, we could not ignore the BT cotton entomology, which had major contribution in socio-economic impact on farmers' community. As BT cotton adapted in India, 162 species of insect pests attack different stages of cotton. The bollworms are most important tissue feeders and highly damaging. 3 types of bollworms are there. American bollworm, that is Helicoverpa armigera, pink bollworm, Pectinophora gossypiella, and spotted bollworm, Ureus vitella, normally referred as a bollworm complex, are by far the most damaging and loss-inducing pests of cotton. Amongst all these bollworm complex, Helicoverpa armigera emerged as a key pest all over the country, causing a high as 80% losses in the cotton. A lot of efforts have been made for alternative strategies of bollworm management and various non-pesticidal, restricted pesticidal and IPM techniques have been formulated, tested and demonstrated. These are slowly gaining acceptance, but so far successes have been restricted and dissemination is slow. Transgenic BT cotton, which evokes inbuilt resistance in the host, is gaining wider adaptability as a means of avoidance of losses due to bollworm, because the technology operates at seed level dissemination and find quick favor among the users. Therefore, BT cotton has already proved useful in countries where it has been introduced earlier. In Indian context also, it is expressed to give a wider base to all other protection strategies in cotton. The non-BT cotton farmers use chemical fertilizers, organic manures, and bullock labors excessively, which results in lower net returns. Technology has been found the major contributor to the total productivity difference between BT and non-BT cotton. Seed cost, yield of BT cotton, and cost of plant protection have been found to greatly influence the probability of adoption of BT cotton. Farmers that used cotton engineer to produce the Bacillus thuringiensis substantially reduced the use of pesticide without reducing the output per hectare or quantity of cotton. This resulted in substantial economic benefit for small farmers. As far as the socio-economic benefits of BT cotton, BT cotton adoption has caused sizable socio-economic benefits for smallholders, farm households in India. The technology has increased cotton yields and profits by 24% to 50%. These effects are similar in magnitude to the ones shown in earlier studies for India. The impacts per acre of BT cotton have been stable over time because of rapidly rising BT adoption rates in India. The aggregate benefits increased tremendously. Countrywide, this technology is now used on 90% of the cotton area. On average, household living standard increased by 18% among BT adopters. Most of these adopting households are relatively poor. Hence, BT cotton contributes to positive economic and social development. These are some glimpses of BT cotton hybrids. In 2002, only 3 BT hybrids, which were developed by the Indian seed company Mahiko and contain Monsanto's Bollgard first technology event Monsanto 531 were approved by the national regulatory authorities. In the year 2004 and 2005, 3 other Indian seed companies which had sub-licensed the Bollgard first technology received approval for the commercialization of several additional BT hybrids. And in the year 2006, the number of approved BT hybrids increased sharply. In addition, new BT events were deregulated by the national authorities, including Monsanto's Bollgard's second technology, but also technologies developed by the public research institutes. By 2011, the number of commercialized BT varieties and hybrids containing different events had increased to over 880. More BT events and greater varietal diversity simply effectiveness against a broader spectrum of insect pest species and better adaptation to different agroecological conditions. As far as the achievement of BT cotton is concerned, in the year 2022, BT cotton will complete 2 decades of cultivation in India. Despite the challenges of misinformation, the technology has enjoyed the confidence of farmers, researchers, and policymakers due to the attributes of genetically engineered hybrid seeds and the results observed in the field in terms of pest control that lead to increased yield and farm remuneration. The extent of achievement can be drawn from the fact that about 11.7 million hectares, that is million hectares under cotton cultivation in the year 2019-20 was planted with BT cotton seeds. There is no doubt that BT cotton has not only benefited the farmers, but also the textile industry, oil industry, and boosted our economy. According to the Director of Economics and Statistics, Ministry of Agriculture, Government of India, over the last decade, cotton yields in the country increased by more than 300%. Pesticide consumption reduced by approximately 50%. Acreage increased by 150%. And the production increased by 400%. It is important to understand that it is not just the technology that contributes to increasing yields. India's farmers face numerous uncertainties and crop management challenges which affect farm yields and incomes, and knowledge of cultivation and correct agronomic practices make a significant impact. What is required today is an increase in extension efforts to help increase knowledge of good agricultural practices among us Indian agrarian communities. Farmers continue to face numerous challenges in their fields, that is increasing labor costs for cultivation, which is more than 40% of the total cost of cultivation in many crops, as per the statistics published by the Government of India, or as pest attacks where crop protection challenges exist. Increasing temperature and climate change are also one of the new challenges for the farmers. Hope against the BT cotton community. Even today, farmers are using a 15-year-old technology to mitigate latest pest incidents in cotton. Indian agriculture today needs new technologies to maintain the competitiveness of its farmers on global platforms, to make drastically changes in the socio-economic impact and impact dynamics of BT cotton on farming community in India. Good day. Thanks to one and all. Thank you very much.
Thank you, sir, for such an informative session. Now, second lecture by Dr. D.B. Diosarkar on the topic Cotton Improvement, special reference to Desi Hirsutum in Barbadians cotton. Dr. T.B. Diosarkar is Director of Extension Education, Vasantrao Naik Marathwada Krishi Vidyapeeth, Parban, Maharashtra. Sir is having 30 years of work experience in different capacity. Dr. Diosarkar has major contributions as a cotton breeder in release of Hirsutum hybrids, namely NHH206, NHH250, and NHH715, and Hirsutum varieties. Regarding Desi cotton, has identified first interspec hybrid, that is PHA46 at CRS Nanded, and it's involved in release of Desi cotton varieties, namely Avara, PA08, PA528, and PA740. Sir also guided 18 MSc and 8 PhD agriculture students. Sir also published 7 research papers and 15 lead invited lectures in different conference symposium. Sir published 165 abstracts in national and international conference and symposium. Sir is also a life member of several professional societies and associations. Sir, Diosarkar sir is also a recipient of several awards, honors, appreciation, and recognition like Devi Lal Award, Best PhD Thesis Award in 240, Best Teacher Award in 212, and 4 Best Presentation Awards. Over to you, sir. Diosarkar sir.
हाँ, आवाज आता है मैडम मेरा? Myself is Diosarkar. Can I start, sir? Madam?
Yes, please.
Okay. Okay, myself is Dr. D.B. Diosarkar, acting as Director of Extension at Vasantrao Naik Marathwada Krishi Vidyapeeth, Parvani. Good afternoon to all. Today's chairman of this function, Dr. Upinder Dhar sir, Vice Chancellor, Shri Vaishnav Vidyapeeth Vishwavidyalaya, Indore, Dr. K. Guru Prasad ji, Organizing Chairperson, Dr. Vinod Dhar sir, Convener, Vinod Shinde sir, Coordinator, Narendra Chavan sir, and my colleagues, guest speakers, Dr. D.N. Gokhale sir and Naresh ji. I am here to present the today's lecture on cotton improvements, special reference to Hirsutum, Desi, and Barbadians cotton. If you see, the cotton is one of the most important cash crop, as already Dr. Gokhale sir has given detailed information about the cotton and how it is beneficial to the farmers. It provides cloth, vegetables, livestock feed, medicinal compounds, energy sources, and industrial lubricants. These are the uses of this cotton, and that's why it is called as king of fiber or white gold. Billions of people are depending upon cotton cultivation, trade, transportation, ginning, and processing. This is occupation of these farmers and persons who are depending upon the cotton. And cotton is the most commercial crop, contributing nearly 65% of the total raw material needed to the textile industry, and 60 million people are involved in the cotton industry. If you see the number of species of the cotton belongs to the family Malvaceae, tribe Gossypii, and genus Gossypium. As you know, there are two types of cotton. One is old world cotton and new world cotton. Old world cotton is also called as Desi cottons, and new world cotton is called as American cottons. And among these old world cotton, Gossypium arboreum and Gossypium herbaceum, these are the two species. Whereas in new world cotton, Gossypium hirsutum and Gossypium barbadense, these are the two cultivated species. There are total 50 number of species, and out of these, only 4 are cultivated. And this cultivation is these species are cultivated in Africa, Asia, South America, Central America, and Australia, and so on. That means if you see the history of this species, only 4 cotton species are cultivated, and these 4 cultivated species are grown in India only. These are the diversity among the species. Number 1 is Gossypium hirsutum. This is also called as tetraploid cotton, and it is also called as American cottons. And area covered by this cotton is nearly more than 70%. Gossypium barbadense, this is also called as Egyptian cotton or long cotton, extra long cotton, and this is also a tetraploid one. Whereas the Gossypium arboreum, Desi cotton, diploid cotton, this is having a diploid chromosome number 2n is equal to 26. And disadvantage of this, both the herbaceum and arboreum, is that both the species are having drought tolerance character. If you see the area in India is the largest country among the world, which is having 133 lakh hectare with 41% of the world cotton area. And in terms of production, if you see the production figures, 360 lakh bales India is producing, which is at par with 371 lakh bales of China. And India is the 3rd largest country to export the cotton than US and Brazil. The per hectare productivity in India is still much lower as compared to the leading cotton growing countries, and this is mainly because of the rain-fed situation. And we have varieties which are not having the drought tolerance character, and area covered by these varieties is under rain-fed situation. If you see the 75% of global production comes from the India, China, US, and Brazil, and Pakistan. These are the major cotton growing countries in the world. If you see the state-wise average hectare land cultivation, if you see throughout the India, total cultivation is 129 lakh hectare, and out of this 129 lakh hectare, if you see the major contribution is from Maharashtra, that is 42 lakh hectare. Nearly 42 lakh hectare area is covered by the cotton in Maharashtra, followed by Telangana and Gujarat. These are the 3 states which are contributing major area in case of the cotton cultivation. If you see Tamil Nadu, it is having only 1.55 lakh hectare, and only the barbadense group is grown in this Tamil Nadu, which is having extra long cotton like MCU and Sui. If you see the production figures, we have seen the area. If you see the production figures, the Gujarat ranked first. 90 lakhs bales are produced from only Gujarat, followed by Maharashtra 86 lakh bales and Telangana 60 lakh bales. If you see the production figures are other than the area. If you see the area is covered in Maharashtra more, but if you see the production figures 86 lakh bales from the 42 lakhs hectare area, this is mainly because low yield of Maharashtra is mainly because the rainfall situation and the varieties which are grown under the light or shallow soils, and that's why yield of the Maharashtra is very low as compared to the other states. And total production of the India is 370 lakhs bales. If you see the productivity of this cotton, we have seen area, production, and if you see the productivity, this is somewhat different from the area and production. If you see, the Rajasthan is a ranking first, 683 kg per hectare. Yield production, 3 683 kg lint per hectare. This is production figure of Rajasthan, which ranked first, followed by the Gujarat and Maharashtra. If you see the figure of Maharashtra, area was 42 lakh hectare, but if you see the yield figure, 349 kg lint per hectare, this is a lowest figure among the other states, and this is mainly already that the rainfed situation and rainfed cultivation is a major problem, and soils of the Maharashtra, these farmers are growing the cotton crop on the light soil or shallow soils, and that's why the yield of this Maharashtra is very low. And second one reason for the low production in Maharashtra is that irrigation facilities are very less as compared to Rajasthan and Gujarat. In Gujarat, if you see 677 kg lint per hectare, this is mainly due to the irrigated area is more in Gujarat and Rajasthan, and yield levels are very high in these two states as compared to the Maharashtra. And total, if you the average productivity of the India is 511 kg lint per hectare. If you see the lint requirement, total lint requirement of the country during the last year to 2021 is 502 lakh bales. Among these 502 lakh bales, 120 are opening balance. Crop production, that productivity 371 lakh bales, and we are importing 11 lakh bales, and total requirement, total production of this country is 502 lakh bales during the last year. If you see the consumption figures, the milk consumption, mill owners are purchasing the lint 286 lakh bales. The small scale industry consumption is 26 lakh bales. Non-miller consumption is 18 lakh bales, and export is 70 lakh bales. This is the picture of these lint requirement to the industry, and total requirement of the India is 405 lakh bales, and we have a balance of 97 lakh bales during the last year. This is again area and productivity. If you see the in 2002, Dr. Gokhale has already we have explained, during the initial stages when the BT was not there in India, that is before 2002, the area was very less, 76 lakh hectare. But once the BT was capturing the area, then it comes to 134 lakhs hectare area is covered by this cotton. And productivity also, you see, if you see the before BT, the production was 300 kg, but after the induction of the conversion program and the release of these BT cotton hybrids and varieties, the production figures in 2013-14, it was 566 kg per hectare. This is the summary of this last graph. If you see the future requirement, what is the requirement of the future in case of cotton? Development of CGMS based cotton hybrid for rainfed situation. This is most urgent need for the rainfed area. Identification, development of abiotic stress tolerant genotypes. As we have seen, the large area is occupied by the Maharashtra, and we are lacking the abiotic stress tolerant varieties. Then BT cotton hybrids and varieties for rainfed situation. This is again one of the lead. The companies, seed companies, private seed companies are developing varieties for developing the hybrids for the rainfed situation. But now the need is to convert the varietal program into the BT for the rainfed situation. Then development of short duration varieties which are suitable for double cropping and suitable for high density planting species and mushing picking. This is again one of the requirement for the one of the challenge for the breeder. The emerging pests like mealybug, pink bollworm, and thrips and leaf curl virus. Cotton leaf curl virus is a major disease in case of North India. These are some of the major problems. We have to fight this, and we have to breed the varieties which are having tolerant to the sucking pest as well as these virus diseases. Then breed for more strength which is required for the high speed spinning. This is again requirement. If you see the number of varieties which are evolved by the seed companies or private seed, public sector, these are lacking in strength. And that's why we have to breed the variety which are having spinnable, which is spinnable at 120 count, more than 80 counts. It is the desirable one. If you need to develop the variety suitable for the organic cotton, this is again one of the new area for the cotton research worker for developing the new variety. If you see breeding objectives at a glance, higher yield, this is a common one. Then earliness is most important because our area is rain-fed and we have required the short duration varieties which mature in 140, 150 days. And this is one of the major objective in case of for increasing the yield in dryland situation, we have to reduce the duration of the crop. Then fiber quality, as already we have seen, whatever the varieties we have developed, these are having better giner, having gening percentage more than 30%, having fiber length more than 28 millimeter, but the strength is very less. That's why we have one of the objectives is to breed the varieties which are having a better strength for spinning to the highest count. Then wider adaptation, this is the most important, resistant to biotic and abiotic stresses. There, as you know, there are, we have already seen these are the emerging new pests, like mealybug is one, and the pink worm is a serious problem. As you know, whatever the hybrids which are released for cultivation, these are having Cry1AC and Cry2AB, Bulgar 1 and Bulgar 2. These are the two types of genes which are involved in the BT cotton, and these all previously there is a resistance for this bollworm. But nowadays, if you see, the resistance for pink bollworm is broken. And whatever the varieties we are seeing, whatever the varieties or hybrids we are observing on the farmer's field, they are susceptible for the pink bollworm. That means why this is happened, because the recommended technology we have not used, the farmers have not used the refugia crops, and that's why the resistance was broken. And as we are seeing, the varieties are susceptible for the pink bollworm. Resistant to abiotic stresses. This is also most important, like drought situation. We have to breed the varieties for drought situation. Synchronous maturity. This is one of the again most important character, because for double cropping, synchronous maturity is most important. And why? Because if the crop is synchronous in maturity, we can make the harvesting early and we can take the double cropping. Quality of oil, again, this is most important, because cotton is also used as a source for edible oil, and oil content is 18 to 19% in case of cotton. But this oil contain the gossypol glands, and this is dangerous to the human being, and that's why we have to breed the varieties which are having a low gossypol content. And VNNK Parvani has developed varieties in case of Deshi cotton, which are having a less gossypol content seed, and producing the oil which is having a less dangerous for consumption. Natural color cotton, this is also one of the objective for the breeder. If you see, these are the common number of breeding methods: introduction, pure line selection, mass selection, pedigree, backcross, heterosis breeding, and mutation, interspecific, and biotechnology. These are the common breeding methods which are utilized by the breeder for the improvement of the cotton or any crops. But if you see, in case of cotton, we are using the heterosis breeding on the large scale, and interspecific hybridization for transferring the character from wild to the cultivated. This source is we are utilizing the interspecific hybridization for transferring the favorable genes from the herbaceum or arboreum to the hirsutum. This method is generally we are using in case of cotton. But if you see on large scale, number of hybrids which are released for cultivation, they are coming from the pedigree method by crossing the heterosis breeding, and varieties are developed by the use of pedigree method of breeding. If you see, as we have seen that these are the number of methods of breeding, and every method is utilized for releasing the variety. Every method is utilized for breeding the variety. For example, introduction is one of the method, and variety is Savitri, which is released by the introduction. Pure line selection, Loy. Mass selection, there are number of varieties are there. Because Norma is there. SRT1, this is a very popular variety in the earlier years. SRT1, this is recommended for the shallow soil and having a good yield with short duration. These are the most important character of SRT1. Mass selection, this variety was developed. Pedigree method, number of varieties are developed as we have seen. The heterosis breeding for hybrids and pedigree method for developing the varieties we are using. And these varieties are PKV081. This is a new genotype which is developed by the Dr. PDK Akola from Maharashtra. LRI 51166, NS615. These are the dominant varieties which are released by the different state for their cultivation. NS615 is released from the Nanded, cotton research station Nanded from Maharashtra. This is having a suitable genotype for high density planting, as well as it is also suitable for drought tolerance character and suitable for the closer spacing. These are the most advantages of this NS615. This is also best combiner for developing the hybrids. Again, this is one of the best combiner for developing the hybrids, NS615. Then mass pedigree selections are also used. Backcross method, heterosis. In heterosis, as we have seen, number of hybrids have been developed by the different universities for their location or for their zone. For example, one of the example we can quote the S4. This is the first hybrid which is developed by the C.T. Patel in Gujarat in 1970. This is having a wider adaptability hybrid. This was continuously ranking first position in Maharashtra, Gujarat, and Central Zone also. Throughout the India, this is cultivated. This is the original hybrid, first hybrid, which is developed by the H into H, hirsutum into hirsutum types. Then next hybrid, which was prominent, was NH44. This was released from Cotton Research Station Nanded from Maharashtra. And most important character of this was released in 1983. And continuously it was growing in Maharashtra and other states also. This is acting as national check in the AICP trial. And this was good yielder, having a replacing capacity among the hybrids, and that's why very stable hybrid was previously. It was very stable hybrid. Now efforts are also made, and we have introduced a BT conversion program in this NH44, and it was released for the cultivation for Maharashtra for the rainfed situation. Then mutation breeding, MCU5, this is again a very good variety, which is having more fiber length released from the Tamil Nadu. If you see the development of diploid cotton hybrid by the interspecific hybridization, how we can use the diploid, how we can use the interspecific hybridization for development of hirsutum by utilizing the arboreum cotton or deshi cotton. Because deshi cottons are having some of the important characters, inherent character like drought tolerance. They are not susceptible for disease and pest, and having a deep root system and showing the drought tolerance character. And this drought tolerant character we can transfer into the hirsutum. Hirsutum cotton varieties are already high yielding, but they are lacking one of our most important character as compared to the diploid one. Though the conventional breeding, we are not making the process of this arboreum and hirsutum because they are unsuccessful due to the having a different chromosome number. As you know, the diploid is having 2n is equal to 26, whereas in case of hirsutum, it is having 52 chromosome number, 2n is equal to 52. That's why there is a there is no chance for crossing between the hirsutum and arboreum. But if you double the chromosome of this arboreum by the colchicine treatment, and make a tetraploid of this arboreum and 2n is equal to 52, then it can be crossed with the hirsutum. By doubling the chromosome of arboreum or deshi, we can make the crossing program, we can make the cross success with the hirsutum for transfer of the character. And then we are utilizing this doubling chromosome of arboreum and producing the autotetraploid nature of this arboreum. It is crossable to the hirsutum, and bigger ball size and super fiber qualities of the hirsutum can be transferred to the arboreum by this method. And if you see the habitation program, this program is successful at VNMQ Parbhani and MPKV Rahuri. The Dr. Dex Pandey sir and Dr. Maitre sir, they have made efforts, and they have made autotetraploid of arboreum cotton PA 9595. This is arboreum 1 having 2n is equal to 26. It is crossed with the Purnima variety, which is a American variety, which is having a high genor. And by making the autotetraploid of this PA 9595, it is crossed with the Purnima Na239, and F1 was produced and backcrossed with the autotetraploid. That means once the BC1 F1 was produced in F2 population, after raising the F2 population, the segregating population was screened, and bigger ball size and more fiber length genotypes were selected at Parbhani level, and the variety PA402 was released for cultivation in Maharashtra, which is having an introgress material from the arboreum and hirsutum. This is one of the unique example of integration of transfer of genes from arboreum to the hirsutum, and development of the diploid cotton PA402, which is having better fiber length as well as ball size, just like up to the like that of the hirsutum one. If you see the characters of some of the wild types which are having, we are using for the breeding program, and these are the number of characters which are donating. These are the donors for transferring the desirable character into the cultivated one. For example, fiber length, we have to improve the fiber length by Raimondi, Inaugural, and so on. For fiber length and elongation, again the Thurberry is there, Anomalum is there. These are the Raimondi. These genotypes we can use for the improvement of fiber, fineness, fiber yield, and gening. For gening, there are a number of wild type sources for improving the characters of the fiber quality of the cotton. These are the sources. Raimondi, this is for length, strength, fineness, bollworm, jacids, bacterial blight, and drought. These are the all characters which are involved in this Raimondi can be transferred into the cultivated one. These are the wild types. Then Anomalum is there. Anomalum for the fiber length, strength, fineness, and bollworm, jacid, and bacterial blight. These wild types can be utilized for transferring their wild character into the cultivated by the backcross method. Then for bollworms, again there are sources which are utilizing for development of bollworm resistance in case of cotton. Then these are the two varieties, Thurberry and Tomentosum. The Thurberry is for bollworm and wilt, and Tomentosum is for drought. These are the sources. Iridium source can be used by most of the centers of AICP. They are utilizing the iridium source for development of CMS based hybrids. And as you know, the first CMS based hybrid, cytoplasmic genetic male sterile hybrid, genetic male sterile hybrid was released as Saguna. And based on the cytoplasmic genetic male sterility, two hybrids from PDKV Akola, they have released hybrid 3 and hybrid 4. These are the contribution of these Dr. PDKV Akola from Maharashtra. They have released two hybrids. Cytoplasmic genetic male sterile lines are used, and they have utilized first time Dr. Tayyab from Maharashtra have evolved these two hybrids, PKV hybrid 3 and PKV hybrid 4, for cultivation as a source of by utilizing the wild source of this aradum. These are the again sources. If you see some of the important diploid lines which are developed in India, some of the only way taking one or two, please. Gauran 6 is this variety, which is evolved in the year 1936. And if you see the fiber length is 26 millimeter, and it is recommended for Maharashtra and AP. Eknath from BA32, Eknath from Maharashtra. This is having a release for the, if you see the gening out turn is more, that is Y1 and this Eknath, both are having, all the varieties are having more GOT as compared to the other varieties, and that's why I have mentioned here, because of the, this is a donor, it also acts as a donor for the GOT. Then if you see the Hirsutam varieties which are released for all India level, and Guri 1007 and Purnima, this is again Purnima, we have utilized in introduction of genes. This is having a character 40% GOT. This is higher. This is generally more than 38% GOT is very desirable for the plant breeder or the farmers also, and that's why the Sahana, it is also having the genic percentage of 40. Purnima is also having a genic percent of 40. As you know, if the yield are increased, if you increase the yield, the fiber content, that means the percentage of GOT get reduces. But in both the cases, in Purnima and Sahana, the GOT is high, as well as these are the high yielding varieties which are developed by the different Purnima for Maharashtra and Sahana for South Zone. These are the two varieties which are having desirable characters. Then LRA 5166, this is again stable genotype, which was evolved in 1982 and recommended for Tamil Nadu, Andhra Pradesh and Maharashtra. This is a stable one. And in ASCP trials, it is also used as a check for the in different trials. These are the important interspecific hybrids of cotton developed in the India. S4, then DCS32. This S4 is H into H, whereas the DCS32 is H into B. Hirsutam into Barbados, interspecific cross. This is evolved in 1981, which is having a GOT 36%. This is the highest genic percentage in case of the Barbados group. If you see the count, the 80s count is here. That means spinability is more in case of the DCS32, and Varalakshmi, Lakshmi, and DCS32. These are the Barbados types which are spinable for the higher count, it more than 80. If you see the S4 also, this is having a 28 millimeter fiber length. If you see all the varieties which are having more fiber length, then GOT is also more than 35, and count is also very high. If you see the general variety which are having the spinning count is 30 or 40 is count. But if you see these hybrids, these are having the count more than 50, 80. These are the some of the achievement. And this Savitri RSR 253 is evolved from the Rahuri, and it is a type of S into B interspecific hybrid. Hirsutam into Barbados, and count is 60. That this is also one of the desirable character of this hybrid. Then these are the again NSB 12. This is released from the Cotton Research Station Nanded, H into B interspecific hybrid. If you see, it is having a count of 80, and genic percent is also more, and fiber strength is 33 G per text. This is again better hybrid, which is having more count, more fiber, and GOT is more. Even it is Barbados, GOT is 33%. This is desirable one. The hybrid 3, which is developed by the Tayyab from Akola, it is having the which is released for the Vidarbha and Gujarat one. Then PHA 46, this is a interspecific Desi cotton hybrid. H into H herbaceum into arboreum. This is a interspecific hybrid in Desi cotton. First released from the VNMK Parbani from Mahbubagh, and it was recommended for Maharashtra, which is having count with better 40% count. Even it is Desi, it is having a 28 millimeter fiber length. That means fiber is also good in case of Deshi cotton hybrid. Then Om Shankar H/H from Haryana, which is having 34% and 40 count. This is also a good hybrid. If you see the Egyptian cotton, Barbadans types, the main features of the Barbadans is having low yield, having less GOT, but the fiber length and micronear is less, micronear is low, and strength is more. These are the most important characters of Barbadans. If you see the Swing, 36 millimeter fiber length. If you see the G per text, 28.48 G per text, and micronear is 2.92. As the micronear increases, spinability increases, and that's why it is spin at 120 count. Then DCS 32 again, it is micronear is 3 and having more GOT. These are some of the important hybrids which are released in case of Barbados type. Then development of high yielding varieties for better fiber quality characters. Understanding the need of the farmers, as we are already saying that the Maharashtra is having more area but very less in 350 kg per hectare. This is low yield, and which taking understanding the need of the farmers in Maharashtra. Vasantrao Naik Marathwada Krishi Deputies involved in the development of Deshi cotton varieties and hybrids of American cotton, and number of varieties have been released for all the zones, not only for Maharashtra. It is also for central zone as well as south zone. If you see some of the important contribution of this VNMQ Parvani in case of cotton, this is at a glance contribution of Vasantrao Naik Marathwada Krishi David Parvani from Maharashtra. And if you see PA 183, this is Sauta. This is having, if you see the characters, this is having GOT. If you see all the varieties, as you know, the varieties which are having Deshi type, these are having low genome. But if you see the recently varieties developed by the VNMQ Parvani, and the GOT of this variety is 93, 39 or 40. 39 or 40% GOT. These are having a better GOT lines which are developed by the VNMQ Parvani. If you see the fiber length again, if you see the previous Deshi cotton hybrid, Y1 or Eknath or Sanjay, these are having fiber length 18 to 20 millimeter. But these recently released varieties which are having the fiber length 28, 27, 28 millimeter, comparable with the hirsutum one, and yield are also comparable with the hirsutum. GOT is also somewhat more than the American cotton, and fiber length is again, if you see the fiber length, it is also more than American cotton. These are the most important, but the strength is less as compared to the other hirsutum and Barbadans. And the micronear is also high in case of Deshi cotton. These are some of the important arboreum cotton, PA 183. These are the release for the, some of the varieties are released for the Maharashtra, and some of the varieties which are also released for the South zone. This PA08, this PA740, this variety developed by the VNMQ Parvani is suitable for cultivation in South zone, Central zone as well as South zone. Again, this PA08, this is having a naked seed. This is having a low gossipal content. As I have already said that we have developed a variety which is having a low gossipal content. That variety is PA08. And these are the varieties which are developed for the Maharashtra in case of variety. Again, NH41452, this is an American variety which is having a 14 count, 14 GOT, and having a count is, if you see, count is very less as compared to the recently released hybrids and varieties. Then if you see, these are the two hybrids, NHS 250 and NHS 206, NHS 715. These are the three hybrids which are released from the in 2015 and 17 for cultivation in case of Central zone as well as South zone. This is recommended for South also. These are the two hybrids which are contributed from Cotton Research Station Nanded, and these are cultivated. These are recommended for cultivation to the central as well as some of the south zone also. If you see, the GOT is more, fiber length is more, and the count is 50s count. That means we have improved the count also. 50s count, 30-40 count is replaced by the 50s count. This is also one of the important contribution of the VNMK Parvani. These are the 615. This is again suitable for the organic cotton SDPS system. Again, this variety is NS635, NS45. These are the hygienor one. Again, these are the photographs of these release hybrids. This is the 615 release for the Maharashtra for the organic cotton as well as the SDPS system. Regarding the BT conversion program, G. hirsutum and G. arboreum, these two species are converted by CICR Nagpur in case of BT, and conversion program of the hybrids which are released by the VNMK Parvani. They are converting the conversion program of these two hybrids in BT BG2 have been started by Maharashtra Seed Corporation Akola, and NS44 was released for cultivation to the Maharashtra. In future, the BT version of G. hirsutum and G. arboreum varieties will be more useful and fulfill the need of the rain-fed cotton. This is the need. Tomorrow's need is development of hirsutum and arboreum varieties in BT. These are the number of varieties and number of hybrids, BT hybrids released by the different seed company during the last 2021. These are recommended for cultivation in different zones, and different companies have been released these genotypes for cultivation in Maharashtra. This is a last figure. If you see, before BT area was very less, and if you see, the BT was 0.29 in 2002. This was the initial stage of incoming of this BT, and the area is 117 lakh hectare. This is a drastic jump in case of area due to the BT. Thank you. This is short about the conversion program and improvement of cotton, arboreum, and hirsutum in case of Maharashtra. Not only in Maharashtra, it is throughout the India. How the things are coming, and what is the requirement of in future regarding the cotton for the breeders. Okay, thank you.
Thank you, sir, for such an informative session and highlight the cotton movement. Thank you very much, sir. Now, today, last and third lead, on the topic cloning.
Dipali madam, speak loudly. Dipali madam.
Yes, sir. Yes, sir. Thank you, sir, for such an informative session and highlights the cotton improvement. Thank you very much, sir. Now, today and last, third lead lecture by Dr. Naresh Silokar on the topic Buffalo Cloning, a tool to multiply India's Black Beauty. Dr. Naresh Silokar is a scientist, Indian Council of Agriculture Research, National Dairy Research Institute, Karnal, India. Sir completed 6 months of Commonwealth Fellowship training in cattle embryology at the Ontario Veterinary College, Canada, and 1 year postdoctoral training on CRISPR-based genome editing in mice embryo at Fly Institute Farm Animal Genetics, Germany. Dr. Silokar has also contributed significantly to establish a simplified, economical, and efficient handmade cloning in buffalo. Handmade cloning is being used to produce cloned and transgenic edited buffaloes in India, and also establish a somatic cell biobank of elite buffaloes. In addition, Sir also has been working on other assisted reproductive techniques such as in vitro embryo production, embryonic adult and induced pluripotent stem cells, cryopreservation of somatic cells, oocytes and embryos, artificial insemination, and embryo transfer. Sir authored more than 14 scientific papers in peer-reviewed journals organized more than scientific trainings, workshops, and meetings. Sir, also a recipient of several awards, including most recent one is Associate Fellowship in 2020 by NAS India. Young Scientist Platinum Jubilee Awards in 2019. Sir, also recipient of Innovative Young Biotechnologist Award in 2018 by DBT India. Young Scientist Award in 2015. Jawaharlal Nehru Award for Outstanding Doctoral Thesis Research in Agriculture. Over to you, sir. Shilokar, sir. Over to you, sir. You can proceed.
Hello.
Yes, sir. Yes, sir. You can start. No problem.
I'm audible.
Yes, sir.
Okay.
Perfectly.
My slides are seen.
Yes.
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 Okay. Thank you, Madam Deepali, for introduction. Nice introduction of mine. It's a great pleasure for me to deliver a talk at the second international web conference that is the theme on the future of food and agriculture trends and challenges. Before me, the two speakers, namely Professor Gokhale and Dr. Professor Dev Sarkar. The both has been talked about the cotton. The first speaker, Dr. Gokhale, has talked about the BT cotton particularly. And the second speaker, Dr. Dev Sarkar, has talked about the cotton again, but that is about the Desi cotton and the indigenous varieties of the cotton. And we know that India has been contributing significantly in terms of the cotton production, and cotton is one of the major crop in the country. So I'm really thankful to Vice Chancellor Dr. Upendra Dhar and the Dr. Guru Prasad, organizing chairperson of this web conference, as well as convener of this event, Vinod Dhar, and a special thanks to Dr. Yuvraj Sindhe and the Dr. Aslam, who is my colleague at NDRI, Dr. Aslam, for inviting me to this web conference to deliver a talk, what we have been doing at the National Dairy Research Institute, Karnal. So my talk, today's I have given the 45 minutes, so I will try to complete within the stipulated time. So my talk, I choose about the buffalo cloning, a tool to multiply the India's Black Beauty. Now, why we call the buffalo is to be Black Beauty, that is the first important. I think everybody is aware that in the Indian agriculture is dependent on not only in the agricultural crops, but also an animal husbandry sector. And today is when the government of India is planning to increase the doubling of the farmer income. So as an animal scientist or as a veterinarian, animal husbandry is an important component of an agriculture. So without the contribution of the animal husbandry to the agricultural commodity or agriculture output in the country or to the farmer income, it's really impossible to increase double the farmer income or to socially or economically uplift the farmers' prosperity. The animal husbandry contribution has been made significantly. And among the animal husbandry, a buffalo is also an important contributor. So in my opinion, I grade the buffaloes to be a much more awesome than any other celebrity. Why? Because the farmers, if you have the buffalo or if you have a cow in your home, then you can every day sell a milk. And that is considered to be the ATM machine to the farmer, because every day you harvest the milk from the animal, sell into the market or your local community, and then you earn the money. And that's a function of the ATM machine to the farmer. If you look at the global population of India, still at the present, the buffalo contribute to the total milk production is 49% of the total milk production in the country. So India is going to cross the 200 million metric ton of the milk the next year. So among that population is around the 49%. That means around the 90 million metric tons of the milk is contributed by the buffalo. And because in India we mix the milk after processing. So there are some companies, they label the milk the cow milk, but the majority of the milk outlets or the milk producers or milk distributors, they mix the milk, either it's the cows and buffaloes, and then sell. So at least the 50% population of Indian population, they drink the buffalo milk. If we talked about the export value of the buffalo meat, the export value of buffalo meat is much higher, is in the last couple of years, the export value is 20,000 crore rupees. And that 20,000 crore rupees is more than that of the basmati rice Indian government or the industry has been earning. That is an export value because we have the legally allowed the slaughter of the buffalo. And we know that because of the Honorable Vice Chancellor has been talked about the organic agriculture. To have the organic agriculture, with this, we need to have these manures or the organic manure to be produced, and the buffalo or the cows, those are the last domestic animals. The best is their dung can be used to produce the vermicompost or organic manure. And that's why the buffalo is considered to be a black beauty of the India. Now coming into what the buffalo population is overall the country, according to the latest, the livestock census is conducted in 2019. The total Indian buffalo population is 109 million buffaloes. So among that, the male population is around the 100 million buffaloes. So and if you have the breedable population, we have around the 54 million buffaloes population. And as I mentioned, is that the buffalo shares the 49% of the total milk production, and meat value is exported. I already mentioned that we have around every year there is the export value is 20,000 crore rupees. Every year the meat industry has been earning from the buffalo meat. And just I would like to mention is that the buffalo are the two type of buffaloes in the India. One is the riverine type buffalo. The most of the buffaloes, for example, the Murra or the Nili Ravi, Surati, Marathwadi, Nagpuri, Pandharpuri, or any other buffaloes, which are the majority of the milk animal, they are the riverine type. They have the 50 chromosome number. The another buffalo, they are the swamp type buffaloes, and the swamp type buffaloes, they are mostly located into the northeastern part of the country. For example, the northeastern state, Assam, Guwahati, and the Mizoram, Nagaland, these places. And the swamp type buffaloes, they are particularly the dual purpose. The milk production is extremely low, but they have been used for the marshy lands there. And on the basis, because basically we think about the buffalo is a milk animal, but is not actually that. Buffalo is not only the milk animal, is also a meat animal in the country, but much more focus has been given to the meat productivity of the buffalo. So, but the contribution of the buffalo in terms of the milk, meat, as well as if you look at the northern part of the India, for example, Haryana, Western Uttar Pradesh, and Punjab, buffalo bullocks, the bullocks or buffalo maize, they have been used to carry the carts to carry over the agricultural communities, for example, sugar cane, the grasses, or any other thing you can frequently find in the northern part of the country. That buffalo has been used for the work power. So that's why the buffalo is a triple purpose animal. They are producing milk, meat, and the workforce. Now coming into my topic, this is just I would like to highlight the significance of the buffalo in the country. So I think everybody, those who have been studying the science, they have been heard about the dolly. The dolly is a famed sheep that's produced in the United Kingdom and Scotland, University of Edinburgh. So in 1996, the dolly has been born, and that the technique has been changed, the paradigm in the term of the developmental biology. So the developmental biology previously thinks that to have to produce the babies, either it is a human or it is a mammal, for example, the cattle, buffalo, sheep, goat, mouse, or any mammals, those are reproduced, there is a requirement of the sperms and oocyte to be united. And once the sperms and oocyte are united, they have been produced in embryos and then animal to be born. But when the dolly's birth, that is produced through a somatic cell nuclear transfer, it has been changed. The concept about the developmental biology or reproductive biology is that without the use of the sperms, the animal can be produced, and in which this method is technically called as the somatic cell nuclear transfer, or called as the animal cloning. So what actually did is that the original animal, the somatic cell, which has the diploid genome, usually the sperms and oocyte have the haploid genome, they united together and the embryos form and then transplant into the surrogate mother. Even if you heard about the lot of the infertility clinics has been established in the country, in which those and the couples, they have difficulty in conceiving babies. So they go to the infertility clinic. So where they have actually they collect the semen, they collect the oocyte, and they in vitro fertilize and produce embryos and the babies. But in case of the animal cloning, it's a different method in which, as I mentioned, there is no absolute requirement of the sperms, but oocyte has been required. Even though the oocyte, the genome has been removed of the oocyte, and the somatic cell has the diploid genome, any body cells can be produced. any body cells can be used. For example, skin-derived cell, urine-derived cell, hair-derived cell, or the semen-derived cells, or any the cells available in body can be used to produce the animal. And that's what we are also at NDRI has initiated this cloning technique in way back in 2004-5, and now we have been succeeding. Now, what are the animal cloning facts? The people, they have been confused. I think Dr. Gokhale has been talked about these genetically modified the cotton, but the cloning is not in genetically engineered animal, in which genetically engineering means what? We are not manipulating the genome of an animal. So that's why the clones are not genetically engineered. Another is the offspring of the clones. For example, the female has been born, they are not the clones. So offspring of the clones means that if the clone has produced and they are naturally bred and then they produce the progenies, that is not called the clones. The aging is a normal aging is a process because everybody is, when initially the dolly was born, the people have been argued, or there is a lot of the controversies that the clones have been now shortened age. But throughout the research, it has been proved that the animal, those are born through the cloning method, they have the normal aging. Also, if you look at the globally, what the status of the clones is that the clones and their offspring products, particularly the milk and meat, are safe for the human consumption. Food and Drug Organization of the USA, which is dealing with this Food Regulatory Authority of the USA, they approved in 2008 that the clone animal product are safe for the human consumption, and absolutely there is no requirement of the labeling of the any kind on the clone animal product. But particularly for the transgenic product, you have to label. There's very few products. For example, the salmon fish is the only transgenic product, particularly for the meat or consumption, that's approved for the human consumption. There are a lot of other varieties of the crops, but they are not for the consumption. But only product, as I know, is the salmon fish has been produced in the produced in the Canada. That fish has been approved for the human consumption. As on today, there are many countries, for example, the USA, Argentina, Brazil, Australia, China, and except the European Union, there are the commercial companies are available to produce the quality animals through the cloning technique. Similarly, for example, in India, in vitro fertilization and embryo transfer technologies has been coming into the Indian. India also has a commercial company similarly to the IVF centers in the human animals have, the farm animals have these commercial companies to produce the IVF, the progenies or the sex semen. Now, what are the method of the cloning? Suppose you have to clone any animal, you have the elite animal need to be selected. For example, you are working on the bull, the somatic cell to be cultured. Once the somatic cell is cultured, similarly, we require the genetic, we require the ooplasm to support the embryonic development. So the ovaries are collected from the slaughterhouse because, as I mentioned, the slaughtering of the buffalo is allowed in the country. And once the slaughter, so we regularly get the ovaries from the Delhi slaughterhouse. And after this, we isolated the oocyte, and these oocytes are the matured in vitro for the 24 hours. After the in vitro maturation, these oocytes need to be enucleated. Enucleated means what? The genetic material of oocyte to be removed, because here we wanted to clone that animal because, and that's why we established the somatic cell which has a diploid genome. And what the method we are using at NDRI, that is called the handmade cloning. So in which the two enucleated oocyte and one somatic cells are electrofused. This is the somatic cell and the two enucleated oocyte. After the fusion of the somatic cell, there is again the process of the genome activation and in vitro culture. Once they have been activated in culture for the 7 days in vitro, 7 to 8 days, after that, those are embryos developed to the blast, they are transferred into surrogate mother. Once the surrogate mother is transferred, they establish the pregnancies, and once the pregnancy is established, then the cows are born. From, for example, from one animal we can produce, technically we can produce the multiple copies because we have the millions of cells. But if you have the ample amount of recipient or your success rate is high, then you can produce the multiple copies. In India, we are producing the 7 to 8 copies from the one animal. I have one video about this, the cloning method, just I would like to share. Is this video seen? Hello?
No, not yet.
Not yet?
Yeah.
No, sir.
Just a moment. Now?
Yes. Replay it.
Yes.
Okay. So this is video about the how we produce the cloned animal at our institute. These are the immature oocyte.
Increase the volume, increase the volume.
No, this video don't have volume.
Okay.
So after the collection of oocyte, these are the in vitro mature oocyte after 21 hour. And this 21 hour of in vitro maturation, after this, if you see here, these are the denuded oocyte which have these cumulus tree, and if you see the bright spot here, this is actually the polar body and the metaphase 2, that's for the genetic material of the oocyte. Then we make them a zona free. These are the zona free oocyte. This, if you see, this is bulging portion, and this bulging portion is the protrusion cone, we call as a protrusion cone. And just behind the protrusion cone, if you see the bright dot here, this is a genetic material of oocyte, that's for the metaphase 2. And then we select the oocyte. So manually selection to be done. Then this oocyte after the under the stereo zoom micro. This is all under process has been done under the stereo microscope. And this stereo microscope, this oocyte size is around the 100 micron. This you cannot see by the your visible eye. Under the stereo microscope, this is the microblade for the cutting of the manually bisecting of the oocyte. So here, if you see here, the oocyte has been bisected into the two parts. One part having the protrusion cone, which has containing the genetic material. Another part does not have the genetic material. And this part does not have genetic material part to be used as a surrogate cytoplasm. So again, we need to have a somatic cell. So we establish the fibroblast cells from the donor animal or the animal that to be cloned. So that animal to be selected and established, then we trypsinize the cells. This trypsinization means we need to make them cell in single suspension. After the single suspension, the one somatic cell is sandwiched between the one enucleated oocyte. And this, you see this for the pairing, when this is the somatic cell has a diploid genome, and this enucleated oocyte where genome has been removed to be one done. After that, under this electric current, these two enucleated oocyte and one somatic cell is sandwiched. So that the genome of the somatic cell is been reprogrammed to the embryonic stages. So here there is a rounding of the rounding mean the mixing of the two cytoplasm. So there is a cytoplasm will mix, they will be completely rounding up, and this is called as in one cell stage embryos. And once they have been one cell stage embryos, these embryos will be activated. So if you see there is mixing of cytoplasm has all the transcription factors that are able to reprogram the genome of and differentiate somatic cell, because somatic cell is fully differentiated. So normally, normal reproduction, the sperms and oocytes are united together to produce an embryo. But in case of the cloning, there is absolute no requirement of the sperms, and somatic cell is sandwiched or injected into the enucleated oocyte. Also, the new genetic material of the oocyte is removed, and that's actually the oocyte supports the development. Once they have been fused embryos, you see the different stages of the fusion. These embryos need to be activated. So activation, normally what happens in normal reproduction, once they have been activated, their calcium level is increased. So we artificially increase the calcium level where the calcium iono 4 and 6 DMAP. Once these been activated, they need to be cultured. This is one of the system of the embryo culture is well of the well. If you see here, these are the cleavage stage embryos. Once they have been cleaved, these are the 8 cell stage embryos at the different cell stages, 4 cell, 8 cell, 16 cell. Then there is a compact morula, and this is actually the stage which achieved is the blastocyst stage, which we have been transferring to the surrogate animal. And this stage, this is called the flat surface. If you see here the compact morula, this compact morula is in stage after the 32 cell stage, and this is a blastocyst. So each blastocyst have ability to produce one offspring. So this is also stage is similar to the human development also. So these are the blastocysts. If you see the black color in the darkest spot comprises for the inner cell mass, and the another color here that is called the trophectodermal cells. And these trophectodermal cells, they gives rise to the placenta, whereas the inner cell mass gives rise to the embryo proper, that is the endoderm, ectoderm, and the mesoderm. And this is again the system of the embryo culture we call as the oviduct. If you see here, this is the compact cell which is red in color, that is for the inner cell mass, whereas the another cell which is a green color, that is called the trophectodermal cells. After that, when embryo is produced, that need to be transferred to the surrogate animal to produce the progenies. And the embryo transfer method, either it is an IVF embryos or the in vivo embryos or any other embryos, they are the common method. So non-surgically, the embryo is loaded into this gun, and once they loaded into the gun, these need to be transferred into the horn of the uterus. So it looks at technically really challenging work, and to achieve the produce the progenies. And once they have been transferred, we do the ultrasonography. So ultrasonography we did here at NDRI to confirm that the animal is pregnant or not. So this video we made when I was a student at the NDRI in 2007-6 at that time. So if you see here, this is ultrasonography machine to be used to confirm that these are the pregnant uterus and this animal is pregnant. And the principle of the ultrasonography is similar to that of the human, and that's this way we produce the clone animals. Just to my presentation back. Yeah, slides are seen.
Yes, sir.
Okay, so this was, I would like to show that how to produce the clone animal. Now, if we talked about the journey of the cloning in the country, particularly the buffalo, in India, the Professor M.L. Madan, who has been the Deputy Director General in ICR, and Dr. Singla, they have initiated the cloning in the country in 1997. And that time they could not able to produce an offspring. But the latter, because of that time, there is the lack of the literature as well as really difficult challenges is there. But similarly, the first clone buffalo in the world is produced by China in 2007, but that buffalo is a swine type. And the world first clone river buffalo is produced by NDRI in 2009 under the leadership of the Dr. Singla and Dr. Chauhan. And that has been laid the foundation stone of the animal cloning techniques in the country. The latter on the several clones produced from the different cell type, the fetal fibrillars, newborn, adult, embryonic stem cell, semen-derived stem cell, urine-derived stem cell, or even the wild buffalo, or the multiple copies has been produced in the recent year. So whatever the method we are using is called the handmade cloning. This method is used in the different species. For example, the cattle, pig, buffalo, goats, and sheep. This method has been successfully demonstrated in different species. So our laboratory and one more laboratory, my previous organization, CARB, these two laboratories in the country, they are working on the buffalo cloning technique. So what we need actually to clone a buffalo, this is for the laboratory in vitro, to produce in vitro embryos, we need a very simple infrastructure. One is a stereo zoom microscope. Another, this is the pipette for handling as well as having the glass capillaries to handle the oocytes and embryos during the manipulation as well as for the during embryo culture. Another, what we require, the electrofusion chamber, microblades, and the electrofusion machine. And ultimately, if you have this facility, as well as you need to have the CO2 incubator to culture embryos. If you have this facility with your institute or center, that can be initiate the cloning and to produce the clone animal. Now we have been working on the cloning of the cattle, or particularly indigenous cows, the ghee, sahiwal. We have initiated recently. Hope it will be in coming year we could able to produce the clone cattle too. So what are how many animals and their status in the country? So the cloning has been working from 2007, 6, 2009 first clone born, and then continuously producing the several clones. At present, India, as if we talked about the male, because our target was to provide the quality semen for the artificial insemination in the field, and that's that has been the target has been assigning by the Indian Council of Agriculture, ICAR, to us to produce the quality bulls. So what we are selecting the bulls that is already progeny tested, and that bulls to be cloned, and then if they have bulls to be cloned, so we can produce the semen from the bull, and that ultimately used for the artificial insemination program. So we have the males, we have the females. At present, India has the 4 females as well as the males. At present, the country has the 16 clone. I think more than the 16 clone. This has been a little bit old data. So the 25 around the clones are there in the country, and that's the 25. For example, the 16 clone bulls are available. So if these clone bulls, they can able to produce 20 million semen doses for the breeding purpose, and that's the ultimate aim. These are the different status. Some are producing semen, some are already delivered the calves, There are some other growings, the 7 clone copies from the superior bull, and the recloning has been done also, the clone to clone. So as well as an NDRI, we have also 5 clone pregnancies ongoing at the NDRI. Now the global status of the buffalo cloning. So globally, there are the different countries, as I mentioned, the India, China, Thailand, and Italy. These are these 4 or 5 countries that are working on the buffalo cloning. But the India is the only country where the more than the 20 clones are produced. The rest of the countries, they have sporadic report, 1 or 2, or just they have been demonstrated for the research purposes, but not for the application or translation. But India, I hope in the coming years, if the government allowed, then the clone bull semen to be reached at the farmer doorsteps. That's the ultimate aim of this organization. So if you look at the efficiency of the different cloning methods, so what, as I mentioned, we use the handmade cloning. We have the embryo rate around 30 to 40%, but the traditional cloning, for example, China, Thailand, Italy, they use the traditional cloning. That method is similar to the method of the use to produce the dolly. In that method, the use is the micro manipulator to produce the clone embryos. If you look at the efficiency in terms of the live birth rate, still we have the low efficiency around the 2 to 2.5% or less than the 6 or 7% at present. We are struggling to have the improved efficiency. I hope with the time we could produce or improve the efficiency and produce the more clones. As I mentioned, India has the 20-25 clones are available. If you have chance to visit the NDRI or chance to visit the CRB, you can have the look on the animal clone. They are physically or appearance-wise, they're absolutely same as the normal animal, except that their genetics is different because these are produced through the cloning method. These are the one of the publications we did at NDRI. Here, what we targeted is to restoration of the elite bulls. So normally in the breeding plan of the domestic animal, I think artificial insemination, everybody knows the artificial insemination. This is the only method that has been reached to the farmer level, except the vaccination. Another the method which when extensively used at the field level is artificial insemination, and that's has been done to improve the productivity of the farm animals through the using the semen of the quality bulls. So what happened when the bulls have been selected to the natural breeding? So it takes the time, 8 years, 10 years to declare that bull to be a progeny tested. These are the programs run in the country by ICR, National Dairy Development Board, NDDB, or all the state institution, or even in the MAPSU is there in Maharashtra. So they run the breeding program. And these breeding programs, so they select the bulls. But what happened when they select the bull at the time, that's 8 to 10 years already in past, because you need to collect or record the milk production of the daughter. So normally in animals, the animal to produce the semen, it takes, in case of buffalo, 2 to 3 years. And when the animal is a gestation period is 1 year. So it's a long period to determine if this bull is really a progeny tested or not. Not like the crops, because you have a lot of the short generation interval, lot of the data can be generated in the crops. But in case of the animal, it's really difficult to generate the data, as well as because of the long gestation time, as well as the animals, they are sporadic. They in one place, you cannot place more animal unless until you have the organized herds. So sample size also be an issue. But what we thought that time, if the bulls to be selected or that bull is progeny tested, but at the time the semen is very limited and the bull is not available, because after 8 to 10 years, bulls either been culled or they have been dead. So can we isolate the somatic cell from the frozen semen? The semen usually have the sperms, 80 to 90% in addition to seminal plasma. But in addition to that, during ejaculation, the semen also has the somatic cells from the urethra, and that has been goes to the cryopreservation. So we thought, can it be possible to restore that animal, which has been highly progeny tested, which is not available, but the semen is available, the semen biobank. And then we attempted is that, and to isolate the somatic cells from the cryophyso semen, establish the cells and produce the clone animal, and that the name we named Rajat. And at the present, we, I think Dr. Aslam is there. When he was here, we inseminated the with the semen of the Rajat, and I think our carving has been done. We have produced the 5 progenies, and this is also to prove that the semen from the semen from the bull that has been cloned from the cryophyso semen has been successfully produced the progenies, and we have these pregnancies from the semen of this bull has been ongoing. So this was, I think, the research achievement we made, and this is really a really significant achievement. This is the only research paper in terms of the cloning technology among all the species that has demonstrated the cloning of the or the restoration of the dead valuable bulls. Another paper we published, my previous organization, I joined the NDRI in January 2021. Before that, I spent an 8 year of my service at the CIRB, where we also initiated this work to clone the superior bulls. So in which we have different parameters we studied, because the people, they have been still not curious about that how the clone behave is that. Are their cellular physiology is normal? Or their embryo development normal, gene expression, the health of the clone bull, the progeny, and then what fertility, health data. So we completely, this study has been spent at least 5 years, because in animal, the gestation year 1 year to become a mature, to come into production 3 years. So in this study, we shows that, and this is the first study in buffalo too, is that the growth, health, and fertility of the clone bull is similar to the non-clone bull. And why we are conducting this study? Because ultimately the organization, that is ICER, is every time they're asking, we need to have the data to demonstrate or to convince the scientific community or policy maker the clones, they have absolutely normal physiology and production and the fertility as compared to non-clone bulls, and the semen has a good fertility so that their semen can be reached to the farmer doorstep. This is one more. Another study we thought about the cloning of the that is the swamp buffalo or the Assamese buffalo. I think this buffalo is really important for the northeastern part of the country. So what we did, we airlifted the tissue biopsy from the swamp buffalo from the Guwahati Veterinary College. They have these Assamese buffalo or swamp buffalo herd there. And then we reached to the Central Institute of Research on Buffalo, Hisar. We established the cells there, use as the donor cell and produce the clone embryos, and then transfer into the foster mother, which is the Murrah. If you see here, the calf has been born from the Murrah as the foster mother or surrogate mother. And now this calf has been mature well, donating semen. Now we are distributing the semen of this bull to the Guwahati Veterinary College for the fertility trials. And once it has been fertility trials, this bull we will recommend it for the breeding purpose to the northeastern part of the country so that the genetic improvement can be done. So this covered by the current Science Journal, as well as it has been aired by the Rajya Sabha TV. So this is, we named this animal to the Sachgaurav. It has been born in the field. The embryos produced at the institute and transferred into the organized herd. And this is the method of reconstruction, singlet method, some of the technical, and the Murrah buffalo saw as the surrogate mother. So some of the couple of scientific achievement we targeted through this, or scientific experiment we targeted through this research. So another study we conducted recently is that about the fertility evaluation of the clone bull. These bulls, they are really fertile or not. So if we wanted to sure is that at NDRI, we have the 4 or 5 bulls, they are under semen production. My previous organization, CRB, they have the 2 clone bulls, and we compare the fertility on the 2 methods, the IVF-based fertility, as well as artificial insemination-based fertility. As I mentioned, we have around the 20-25 pregnancies ongoing, and these pregnancy 5 already born. The animals, their calves have been born, and more to be born. But before that, we done the artificial insemination of the 1 clone bull named Swan, Hisar Gaurav, and recently we done the Rajat also. So there are more fertility, and founding that on the basis of whatever the data we have. So we shows that fertility of the clone bull is similar to the non-clone bulls. And these 2 publications, so this is one of this, and the previously our scientific report publication, they have been help us to suggest that, and we are happy to share if anybody wanted to do the field trial or artificial insemination trial of the clone bulls, which is available. They can approach to the NDRI director or the CRB director to have the semen of the clone bull, and they can do their independent trial at their farms or at their organization to again the show is that these animals, they absolutely have the no problem. These are the recent achievement from the 1 animal. We produced the 7 clone copies from the 1 animal, the 100% genetically identical. So everything has been scientifically proven. So parentage need to be done. We cannot publish is as that these are the clones. So we need to have parentage to be done. We need to understand some of the physiological tests, as well as some of the genetic tests, BAL, citrulline, other things. These are the normal standard practice to be done to characterize an animal to be cloned. We done everything, and this has been highly covered by the Indian Council of Agricultural Research. Similarly, the clone bull has been produced in 2015 at the CIRP, that named as Hisar Gaurav. So we thought to, can it possible to again clone the clone bull, that's called the recloning, and it has been successfully done. And this calf now is 1 year of age, and in the next year, coming year, all these bulls, they are going to produce semen. So there's a huge amount of semen to be generated in the country from the clone bulls. And we are regularly approaching to the Department of the Animal Husbandry, Government of India, and Indian Council of Agriculture Research, that the next to be done to these clone bulls. And I hope all the agencies to be considered this technology to be used for the farmer welfare. So in addition to that, we also established somatic cell repositories, so as a biobanking of the somatic cells. This has been available at the CIRB. If anybody interested to have the worked on the somatic cells or the buffalo, they can approach to the director. The cells will be made available to them. So what the journey of the buffalo cloning in the country. So first, India's clone was produced in 2019 at Indian Council of Agriculture Research and National Dairy Research Institute under the umbrella of ICR at NDRI in 2009. The latter one, if you currently the embryo production rate is 30 to 35%, which is acceptable. But what we have been lacking at the live birth rate, the 6 to 8% only. And what our aim was to increase this live birth rate to 20 to 25% to make this technology more viable. At present, what the challenges we have, the pregnancy losses mean abortion, the 20 to 25 to 30% or abortions are there. So we are working scientifically to reduce the abortion rate and to improve the live birth rate. So different clones are produced from the skin-derived cells, stem cells, urine-derived cells, semen-derived cell. As of 2021, the 21 clone buffaloes are available, of which 16 are the breeding bulls, which are alive. So in the two institutions, one is the NDRI and other is the CIRB. So our research studies from the last 10 years or decade, what we proves that the clones that attain the maturity, that have the normal growth, health, fertility, and production. In addition to that, recently we also initiated the quality control or quality assessment of the clone buffalo milk, and we also found that the milk, the quality of the clone buffaloes are found normal. That is absolutely similar to that of the normal animal produced. So now the question is that some of the policy issues, that why we need the cloning technique. That's the first most questions, why actually there is a need or not. If you look at the global population of the country, we have around 130 million breedable female population. It includes the cattle as well as buffaloes. If you remember the second slide in which I mentioned the 54 millions of buffaloes. We also have the cattle. So what the government is planning to increase the coverage of artificial insemination. So at present, we have the 30% AI coverage. What does it mean? The 30% of only breedable female, they are inseminated through the artificial insemination technique. So what we are planning, because to upgrade the population at a faster rate, the animal to be inseminated to the 100% coverage. What we require to semen doses demand, if we have the 30% AI coverage, we require the 99.75 million semen doses. If this coverage to be increased to 50% or to the 100%, for example, 50%, we require 166 million semen doses. If there is 100 million semen dose, so 100% coverage, it requires the 332 million doses. This has been calculated that 2.5 insemination per conception. What actually semen available in the country? Availability of the semen in the country, either it is an ICR, either it is state government, or it is an NDDB. So what the total breeding bulls is available in the country, 2525. The semen that is produced in the country at present is 88 million. So even if you have, that is compensating the demand for the artificial insemination to the 30%. If we wanted to increase, then the number of bulls required to be much higher, as well as the demand of the semen is much higher. And thus there is a huge demand of the quality bulls to be produced. as well as the semen doses for the breeding program. So bulls to be produced by different assisted reproductive technology. One is the natural mating through the embryo transfer technology also, and through the cloning. But what happens if you go for the conventional breeding plan, in which the bulls to be produced by the natural mating or artificial insemination, and then screen and determine and project and then declare to be progenitors, it takes 8 to 10 years. And if you go through the conventional breeding plan, it will take decades, and that will not compensate the demand of the quality bulls. But if you use the cloning technology to multiply the already proven bulls, because the genetics we are selecting at any age, and that genetics to be used, and that will fasterly multiply of the already known genotype. And that's the ultimate aim of this technology, is that the faster multiplication of already known genotype. So we select the already proven or elite bull to be a multiplied. Now, what we are doing at the NDRI, we have the populations of the animals in the country. Only the few population, I think you people has been heard that some cows or some buffalo, they are giving the higher milk yield. But similarly, there are the bulls. They ultimately the genetics has been governed in particular the milk contribution in the herd. 60% of genetics in the herd has been contributed by the bulls. So from the population, we identify or select the high genetic merit bulls, and these high genetic merit bulls either is progenitor state or the whatever the data available with the organization or the farm, we select it and try to multiply the multiple copies. So because these copies, this called the Xerox copies, they have the identical genotype, because the genotype will not change. So whatever the genotype of the high genetic bull we selected for the cloning, the same clone progenies or clone bulls they have. And once these clone bulls to be come to semen production, semen to be produced, and this semen will be used for the artificial insemination. And that's why the demand of the quality semen as well as genetic improvement in the buffalo to be achieved through the use of the cloning technology. Now, how to implement this cloning technology? That's again because this is not yet been reached at the farmer level. So we plan how to implement. What happened, I just first described the conventional method of the producing the offspring in the farm or offspring at the farmer doorstep. What happened, declared proven bull is there. Declared proven bulls means the quality bull which has been used for the breeding purpose, go for the classical breeding for the artificial insemination and to produce the next generation offspring. But how many progenies can be produced from that declared proven bull? Because that is only one bull is available for considering the example of one. So this clone bull, this will produce the limited progeny in the next generation calves, and that will not upgrade the global or the total population of the country. But if you go for the cloning technology in which we have the declared proven bull, so we need to multiply, for example, 1, 2, 3, 4, 5, or whatever the copies can be produced, these will be multiplied. And this, when the clone copies will multiply, this actually the clone bulls to be sent for the classical breeding program. Because from the one bull, for example, we produce the 5 copies of the one proven bull in Haryana. The one bull to be sent to the Maharashtra, one bull to be sent to the Madhya Pradesh, one bull to be sent to the Gujarat, one bull to be sent to the UP or Bihar. And this way, the different parts of the location, what happened at the present, the bulls that has been produced in the one part for one region, either in Vidarbha region, that bulls to be utilized in that Vidarbha region only, or the some parts of Saurashtra or any other region. But if we have multiple copies, we have a possibility to use that copies, because these are copies are genetically identical, and these copies to be used as a different part of the countries. And through the conventional breeding, again, you need to be understand that the clone bulls to be used for the conventional breeding. The cloning method cannot produce the billions of copies. So we can produce the multiple copies of the elite animals, and this elite animal germplasm or the seeds, for example, the semen, to be used to produce the next generation progenies. And that's why this way the next large number of next generation cows which has been elite in nature or highly productive can be produced. So just an example what the current situation we have the 16 clone bulls at present. So approximately one bull in the entire life can donate 1 lakh semen doses. So 16 lakh semen doses can be produced from the 16. We are talking about I'm talking about the current situation. It may be 25 or 30. So from the 16 lakh semen dosage, 6.4 lakhs next generation offspring. 6.4 lakhs means what? 2.5 insemination per calf. This is the standard, or it has been whatever the conception rate we are achieving at the field level, that can be achieved 2.5 insemination per cow. So 6.4 lakhs next generation offspring can be produced from the 16 clone bull which are available in the country. So if we talked about the how much population at present, the 15% of Haryana buffalo population can be produced through a use of the clone bull semen, and that's the we are awaiting. Once it has been approved, it will be easily used to disseminate the semen to the different part of the country. This is our plan to implement the buffalo cloning technology in the country. Now, the status of the buffalo cloning worldwide, what is the status is there? In USA, there is a no specific regulation. You can use the cloning technology. There are several commercial companies available. Transgenic Genetic, Viagene, they are commercially doing the cloning of not only the cattle, but the cats, dogs, and pigs for the research as well as for the purpose. Suppose anybody interested or requested them to clone their cat, they can do it. In USA, it is allowed for the breeding purpose. So it is legally allowed in the USA. There is absolute no requirement of the label the clone bull semen or clone bull oocyte or embryos to be either exported or used for the commercial production. In case of the Australia and New Zealand, there is no absolute specific requirement and commercial companies are available. In Argentina, the cloning technology is available for the breeding purpose and commercial companies also available. One of the company from the Brazil, recently government wanted to import the Gir cattle from the Brazil, which has been way back has been exported from India to the Brazil. And this one company, the ABS company, they have been well established and they wanted to use this assisted reproductive technology in the country. In China, again, no specific regulation, large scale production ongoing. What happened in India? So in India, we are very limited research has been done to the only two research organizations, that's an NDRI and CRP. We don't have any guideline yet for the breeding purpose, and that's ultimately our aim was to convince or to demonstrate or to convince to the regulatory agencies to recommend the clone bull semen for the breeding purpose. But in addition to what the other countries is that USA, Argentina, Brazil, China, they have been using the cloning technology. There are some other countries they have been constrained or they have been not using this technology because of their ethical concerns. For example, European Union. So in European Union, there is a complete ban on the commercial application of the cloning technology. So you cannot commercially use this technology to produce the multiple animals. But for example, USA it is legally allowed, but in case of the European Union, they are banned. But what they allowed, if it suppose the food is produced in USA, if they wanted to sell in the European Union, that food to be treated, for example, milk from the clone animal produced in USA to be sold at European Union, that need to be labeled as the novel food. So similarly, in case of Canada, again, the food, if anybody wanted to sell the food into the Canadian market, that food, either it is a meat or milk, need to be labeled with the novel food. This is a recent available status of the clone animal worldwide. In India, we are still do not have any guideline. If we have whatever the guideline government will decide, that will accordingly we proceed. In addition to that, we also initiated the transgenic animal production. This is about the cloning. So we produce the transgenic animals we have wanted to produce. So transgenic animal production is really tedious and difficult job in farm animals. It's not like the crops, because crops has been different physiology or different management or different things. But in crops, in animals is really difficult. So at present, India does not have produce any transgenic live animal. We have the transgenic crops, a lot of transgenic crops, for example, BT brinjal, BT cotton, CRISPR technology has also been used, but in India, we don't have yet produced any live transgenic animal. So either it is cattle, buffalo, sheep, and goat. So these have been in vitro work we initiated. If you see here, we inserted the reporter gene, is for the venous gene, into the somatic cells, and these somatic cells to be used to produce the clone embryos. If you see here in this side, there is a labeling of the or expression of the green cells, and these are the transgenic embryos. Because to produce a transgenic animal, we need to have an approval from the IBSC or RCGM. We are working on that and hope in coming years, NDRI could able to also produce a transgenic animal. So what currently I'm working at NDRI. So one is major project. My project is the buffalo cloning. In addition to that, we also initiated the Crispr editing. Crispr is a technology that has a potential to transform any industry, either it's a medical or the agriculture or the farm animal or other thing. What they actually CRISPR is a cluster regularly short palindromic repeat. And this technology has a potential to manipulate the gene. If you wanted to, for example, if anybody wanted to correct the sickle cell anemia, previously it's impossible. But through the CRISPR technology, it's possible to correct the sickle cell anemia at the embryo stage. In this, what happened? This CRISPR has been worked to target gene, and you can manipulate. You can replace one nucleotide. You can replace the complete gene, or you can insert the any gene. There are the different applications: the fiber production, reproduction trait, milk quality, meat production, disease resistance. We are talking about the One Health concept in the world, because the animals, some of the zoonotic diseases, they are transmitted from the animal. For example, the corona is the best example. The coronavirus has been evolved from the wild animal and then migrated to the laboratory to some of the host, and then wild fish market, and then to the human. Similarly, the tuberculosis is one of the example in the country. Government of India wanted to eradicate the tuberculosis by 2025, but without considering the fact that the bovine tuberculosis or the TB, it is a human can transmit TB to the cattle and buffalo and the cattle can transmit the TB from animal to the human being. Because in the India, in the rural villages, we have the very close association with the animals. So if you neglect the tuberculosis of these farm animal, we cannot eradicate the tuberculosis from the country. Similarly, there are other zoonotic diseases also. So One Health concept. So this technology, CRISPR technology, can be used to produce a disease-resistant animal. What currently we are working at the NDRI. So we have three projects I'm working. One is a project is a production of double muscle mass to increase the meat yield of the buffalo, goat, and sheep. We have the huge demand of the goat and sheep meat in-house consumption. I think majority of the 60 to 70% Indian population, they are non-vegetarian. And to mitigate the demand, because population increasing day by day, we need to adopt the biotechnological interventions to mitigate the demand of the food. Similarly, for buffalo, we don't have the in-house consumption of the buffalo meat, but for the export value, we require the buffalo, and that buffalo slaughter is available. So we are knocking out the one gene that is for the myostatin, and the gene is regulation of the muscle development. So we're working on the production of double muscle mass animal, and we use the CRISPR technology to mutate the myostatin gene. Similarly, we worked on the bovine respiratory diseases in buffalo to produce the bovine. These are the disease in buffalo in which similarly for the hemorrhagic septicemia, a group is there. There's a disease. When the buffalo infected with this disease, the leukotoxin secreted by that bacteria, anemia hemolytica, and that cause the leukolysis and lung damage. So I will not go into detail how we work, but just to summarize what we have been working in terms of the CRISPR editing in buffalo. Another project we are working on unraveling of the developmental gene in buffalo. These are basic research. What are the genes responsible for the embryonic development in buffalo? So we're working on these aspects too. So these are our new recent initiatives at NDRI. So before the end of my talk, what are the challenges we have? The challenges we have is at present, we have the live birth rate in case of the cloning method is 6 to 8%. And this 6 to 8% live birth rate, we wanted to increase up to 30 to 35%. So other challenge is that we need to generate more data, because the agencies, those are approving agencies, they every time they're asking the field trial data or other trial data. We are giving the semen to the farmers with the consent of their farmers. If anybody interested, they can use. So we need to have the more genomic data on the clones and the progenies, fertility data and production data, how the productivity of the animals, of the clone animals are and the progenies. What the challenges, major challenges for us is to convince how can this clone bush semen to be reached at the farmer's doorstep. And if you, that's why we need the national policy on this. So the scientists from NDRI, my team, scientists from CIRB, they are working and convincing to the ICR and national policies that, and in hope if everything goes well in coming years, the policy will be made and then semen reach to the farmer doorstep. But that is still the challenge for us. The more other futuristic aspect of this technology is that how to explore the buffalo cloning technology for the gene editing, the CRISPR technology. This technology and the gene editing, they have worked together, or they have merged together, and they produce the technical advances for the future. For example, the production of disease-resistant animal. For example, tuberculosis-resistant animal. China has produced TB-resistant cows. And similarly, there are other animals they have produced, but we are also working on that. If we succeed, everything goes well, or we have some leads on that aspect, so we also could able to produce the transgenic disease-resistant animal. Conclusion of my talk: the buffalo cloning technology is a valuable breeding tool to complement the artificial insemination to improve India's buffalo germplasm. I must mention the word complement. So complement, it will not replace the artificial insemination at all, because the artificial insemination reached to the at the ground level. Not only assisted reproductive technology that reached to the farmer level is artificial insemination, no embryo transfer technology or no cloning, but it will definitely complement to the artificial insemination to mitigate the demand of the demand. And this technology can be used to produce the transgenic and the genome edited buffaloes in future. So before closing, I would like to acknowledge this funder of this project. This has been from last 10 to 12 years, the Indian Council of Agricultural Research. They have been supporting this research work at the NDRI and other institutions, CARB. The Department of Biotechnology also supported the giving the grants. The Department of Science and Technology, and to my both organizations, the NDRI and the CARB, they have been generously supporting to this work. The researchers from the different team, they're my teachers, they are now retired, but we are continuing their legacy. The Dr. Singla, Dr. Chauhan still is the director of the NDRI, is here. Dr. Palta, Dr. Manik, and my colleague, Dr. M.K. Singh, and I both work together, and we continue this activity at the NDRI. My previous team at the CIRB, Dr. P.S. Yadav, they are still there at the CIRB, they are working. Dr. Sharma, Dr. Dharmendra Kumar, and Dr. Monica Saini. So these people, they are working at the CIRB to continue the buffalo cloning technology. Thank you very much.
Thank you, sir. Thank you, sir, for such an informative session, and also to aware us about the buffalo cloning. Thank you very much, sir. Now, I would like to request Professor Vinod Dhar, sir, convener of VAKSANA 2021 and head of Shri Vaishnav Institute of Agriculture, Shri Vaishnav Vidyapit Vishwavidyalaya, Indore, for vote of thanks. Over to you, sir. Vinod, sir.
Thank you very much, Dr. Dipali. Now, before it's my privilege to offer vote of thanks to the dignity all present on the platform. But before I read out the vote of thanks, I would like to say something about my institute, because I feel I would be failing if I don't speak about my institution. Sri Vaishnav Institute of Agriculture, Indore, is a constituent institution of Sri Vaishnav Vidyapit Vishwavidyalaya, Indore, and commenced conducting classes of first year of 4-year degree program in agriculture from the academic session 2018-19, leading to the degree of BSc Honors Agriculture. Students here are imparted teaching and training in theory, besides hands-on training, as well as honing skills to ensure world-class quality and create higher levels of intellectual abilities in them. The institute has also commenced 2-year full-time postgraduate program in genetic and plant breeding and agricultural entomology. And we are looking forward to starting several other postgraduate programs. Sri Vaishnav Institute of Agriculture also hosts the Center for Vocational Studies, which imparts training in organic farming, mushroom cultivation, and other skill development courses, the emphasis of which is very much in vogue in present times, as per the guidelines of the Government of India. So, not failing in my duties, as I have to offer my vote of thanks to the dignitaries present on the platform. I express my sincere thanks to Dr. D.N. Gokhale, Director, Instructions and Dean, Vasantrao Naik Marathwada Agricultural University, Parbhani, Maharashtra, Dr. D.B. Deo Sarkar, Director, Extension Education, Vasantrao Naik Marathwada Agricultural University, Parbhani, Maharashtra, and Dr. Naresh Sialokar, Scientist, ICAR, National Dairy Research Institute, Karnal, Haryana, India, for being gracious enough to accept our request and sparing some valuable time from their busy schedule. I am sure that we all have benefited from their informative lectures and that participants may have become aware and more knowledgeable and taken the note, or you may say clue, about the research that needs to be pursued in various fields for sustainability of food and agriculture, not only for human population, but also for other living beings. I express my sincere thanks to worthy Vice Chancellor, Directors, Dean, Research, Head of Institutions, Head of Departments, and entire faculty members of Sri Vaishnava Vidyapith Vishwavidyalaya for sparing time from their busy schedule for participating in this two-day conference. I express my sincere thanks to Director, Head of Department, Engineers, Technicians of Sri Vaishnava Institute of Information Technology, Indore, for their technical support and smooth conduct. Last but not the least, I express heartfelt gratitude to faculty members of my own institute, Life Sciences Department, and also to Dr. Dipali Saxena, who has been the Master of Ceremony for this event, who are involved in conduct of this conference, and participants who showed interest in listening and registering for this event. I thank you all once again. Thank you very much.
Thank you, sir. I'd like to request all the people present here, please stand up in their position for the national anthem. I request the technical team to play national anthem.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you. Thank you all for giving your valuable time. Now, after lunch break, technical session starts. Please join for oral presentation as per schedule. This concludes today's inaugural program. Thank you all. Thank you.
Thank you very much.
Okay, thank you.
Thank you all.
All the best.
Thank you so
Good
much.
luck.
Thank you.